Example 1. All right. Example 1. All right. Given a max heap with, let me say 1,000 nodes, okay? Yeah. 1,000 nodes. Sorry. Now I want you to calculate. Yeah. Find the smallest possible index for a node with height 3. Okay, yeah, this question. Because height 3 nodes, there are a certain number, right? Yeah, certain number of nodes with height 3. And in those nodes, we need to find one with the smallest possible index. Not the largest, smallest. That question, okay, yeah. Yeah, it's pretty easy, yeah, but I need to show you how to do it. All right, solution. Yeah. Let me draw a diagram. Yeah. And we have the formulas. Diagram, okay? The valid locations for all our heap nodes. Yeah. 1, the root location, 1. The last location, 1,000. All right, yeah. But now height 3. So each number equals 3. Yeah. First, we need to find the range for. We need to get a range for the height 3 nodes. Height 3 nodes. We have that formula, right? Yeah. So remember, flow function n over 2 to the 4, right? Plus 1, lower bound. That range. Upper bound n over 2 to the 3rd, a high number. The formula? Yeah. High number plus 1. Okay? Yeah. All right. Yeah, if we draw that range somewhere, okay? Yeah. Let's say this part, that's the range. So this location, n over 8. Because n is 1,000. N over 8 here, 125, right? 1,000. Yeah. Over 8. It's an integer, it's a flow function, 125. Yeah. Then, this location. This location is the 1,000 over 16 plus 1. What's that? Flow function. Yeah, 125 over 2, 62, right? Yeah, because 62.5. So 62. 62 plus 1, yeah, 63. So this location is 63. Okay, 63. Yeah. So you can use the calculator if you need. Yeah. Yeah. So here I just use my mind. Yeah. If I'm wrong, you can let me know. Okay. Yeah. Yeah. Because 1,000 over 8, that's 125. 125 over 2. Yeah. 62.5. Right. Floor function 62. 62 plus 1, 63. Yeah. So this is the answer. Yeah, because this is smallest index in this range. Yeah. This is answer. Yeah. All right. Yeah. Yeah. Very easy. Yeah. For the first example. Yeah. Second example. Yeah. A little hard. Yeah. All right. Let me show you the second. Harder than this one. Example 2. Example. Given a heap with n nodes, here this n number is unknown. We need to calculate this n number. So with n nodes, all right, assume that there are a variable, a leaves, and B nodes of height 1. You know the meaning of height, yeah, in this heap. All right, the question. All right. Oh, one condition. If we know that A plus B equals 48. Okay, yeah. The question, what are the possible values for n number? Okay, right? This question, yeah, little harder than the first one. Solution, but not too hard. Not too hard. Yeah. First, because we have A formula and B formula, right? Here we need to use exact formula. Yeah, we should not use approximate formula. Exact formula. So what is the exact formula? Number of leaves. By the number of leaves, that formula exact. A equals ceiling function of n over 2, right? Yeah. You have another one. Yeah. Yeah. Yeah, but this one looks simpler. Yeah. B, what is the exact formula for B? B equals height 1. Height 1, exact formula. Yeah. We derived floor function of n over 2 minus floor function of n over 4, right? Yeah. That's the exact formula. Yeah. Then we need to set up equations. Yeah. So what is the equation? This is equation. Okay, all right. So then A plus B, so that's ceiling function of n over 2 plus B floor function of n over 2 minus equals 48. Here we need to solve this equation for n. For the harder part, you have 3 floor or ceiling functions. Yeah, so that's not very convenient. Yeah. Yeah, so we want to find a way to make the equation more friendly to us. Yeah, more friendly. Yeah. Yeah. So that's the main point here. Yeah. All right. Yeah. First, can we combine the first 2 terms? Do you know the sum of the first 2 terms? Yeah. We have a formula. Yeah. In our notes, I give you this formula. Yeah. And I give you the page 477 in appendix of our textbook. Yeah. You can also find in the notes n. Yeah. So we can simplify the sum of the first 2 terms. It's n. Yeah. Much simpler. Yeah. So let us update the equation. The equation becomes m minus floor function of n over 4 equals 48. Yeah. Simpler than before, yeah, but still you have a floor function expression here. Yeah. All right. So we want to further simplify. Yeah. Yeah. We want to get rid of that floor function. Yeah. Yeah. To make it more friendly. Yeah. All right. But how to? Yeah. You have different ways. Yeah. Here I give you one way to do it. Yeah. All right. One condition, because here we use the floor function. We know the floor function n over 4 floor less than or equal to the original function without floor, right? Yeah. Less than or equal to. Okay. Yeah. Then we do subtraction both sides. Yeah. M minus n over 4 floor. Because you do subtraction, it should greater, right? Yeah. Because you might smaller. Greater or equal to n over n minus n over 4, right? Yeah. 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 Because we need to switch the direction of the inequality sign. Right? Yeah. And this equals 3n over 4. Yeah. But this number is 48, right? Given. Okay? All right. Then our inequality becomes 3n over 4 less than or equal to 48. So we can find the range of n. Relation 3:16. So n less than or equal to 64. Then we need to find those numbers. Yeah. Yeah. In this range, n less than 64. What are those n's in this range that can make this equation true? Yeah. That's the answer. Yeah. All right. Let's plug in n equals 64 first. You plug in n equals 64. 64 minus floor function 64 over 4. Yeah, because 64 minus second term 16, right? Yeah. 16. 16 equals 48, right? Yeah. Yeah. So that is the solution. Okay? All right. Then, because you need to find all such n numbers. Yeah. If you just find one n, still not enough. Yeah. So you need to find, all the possible values for n. Yeah. Right? Yeah. Then you try next one, 63. Yeah. So this question like this, you may try 63. Okay, and see if it still works. Yeah. This time 63 minus 63 over 4 floor function, 63 minus 15, right? Yeah. Also 48. Works. Okay, works. So this is second answer, solution, second. But more 62, yeah, when you go down one by one, but now you will see, 62 won't work. Because the first term is reduced by 1, but second term, no reduction, right? Yeah, because 62 over 4, floor function still 15. Yeah. Second term, no reduction, but the first term, at least every time you reduce the n number by 1, the first term is reduced by 1. Yeah. First term reduced by 1, but second term keeps the same. So definitely, it does not hold anymore, right? Yeah. So there, another one, another reduction, but the second term reduction very slow. The first term reduction very fast, one after another. So you will see after 63, no smaller n numbers would make it work. Yeah. So your answer is these two numbers, 64 and 63. Okay? That's the second question. Yeah. All right. In your final exam, you will have two similar questions. Yeah. But the first one, I think it should be relatively easy for you. But second one, try to understand this example. Okay? Yeah. If you can understand all the details of this, so then you can solve it in the final, with different numbers. Yeah. So I will give you, the number here is different, but the idea is the same. Yeah. Okay. All right. So this is the B.4. Yeah. Next, I want to go to B.5. Yeah. B.5 we call a partial merge operation. Yeah. So we have at least one final question. We need to use this result. Yeah. Okay. So I want to explain what's the meaning. What's the meaning of partial merge? Merge, right? Our standard merge operation. Yeah. So we start with our standard merge operation. Yeah. But we do not complete the whole merge operation. We stop somewhere in the middle. So that's the partial merge operation. Yeah. For many questions, we need to do this kind of partial merge operations. Yeah. So let me give you an example here. All right. Yeah, here I do not write the whole question. Yeah, I want to save some time. Okay. Yeah. So I do not write a complete statement. So I'll give you an array with 7 elements: x1, x2, x3, x4, x5, x6, x7. All right? Yeah. Then I also give you some initial condition. Yeah. Initial condition, that is x1 less than x2 less than x3 less than x4. That's the first condition. Second condition, x5 less than x6 less than x7. Okay, all right. Condition two inequalities. Question: what do you need to do? What do you need to do? You need to find third largest element. All right? Yeah. So with minimum number of comparisons for the worst case. So I do not write that part. Yeah. So that's our usual requirement. So I don't want to repeat it. Yeah. So you know what we need to do. Okay. All right. So here, there is a simple way to find that solution. Yeah. Simple way. Yeah. So that is the partial merge idea. Yeah. So yeah, let me talk about that idea. Yeah. Solution. Yeah. So here we apply that partial merge idea. Because here, two ordered subarrays, right? Yeah. That's the typical situation when we merge two ordered arrays. So we can do the merge. But here I do not ask you to sort the whole array, right? Well, I do not ask you to do that. Yeah. So you don't want to do the complete merge operation. Yeah. Yeah. Not necessary. Yeah. So you want to save as many comparisons as possible. Yeah. So for that reason, we do partial merge. We do a few steps. Yeah. After we get third largest element, we stop immediately. Yeah, because you get what you need. Yeah. Yeah. Stop immediately. All right. But when we apply the partial merge, yeah, somewhere in the middle, yeah, partial merge. Yeah. So here you have two subarrays. Let me draw a diagram. Yeah. So the first subarray, okay? Yeah. First subarray. Yeah. Second subarray. All right. But when you merge here, we need to view this step. Our standard merge, we compare the two smallest elements, right? Yeah. So here I call it, we do the merge from low end. Yeah. Low end. Okay. All right. But can we also do comparison from the, two largest element from the high end? All right? Yeah. Yeah. We can do that. Yeah. We have two different ways. Yeah. But here we need to find the largest. That means we need to do it from the high end. Okay? Yeah. Yeah. So when we do the comparison, comparisons from the high end. Okay? One comparison, yeah, because after one comparison, you get the largest, right? Yeah. One largest element in place. Yeah. One largest in place. All right. Another one comparison. Second one. Second largest in place, right? Yeah. So you find second largest. Yeah. Then the third comparison. You get third largest in place, right? Yeah. Third largest element. Then, because after we get third largest, we should stop immediately. Yeah. Don't do further comparisons. Yeah. We're done. So that's what we call this partial merge operator. Yeah. 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 Stop immediately after you get what you want. Yeah. Yeah. So this example. Yeah. This simple idea. Yeah. Okay, simple idea. Yeah. So in the final, you will have a similar question like this. try to understand the idea of this question. Yeah. Otherwise, if you do not use this idea, first thing, you need to do a lot of comparisons. It's very time consuming. Yeah. Very time consuming. You need to spend a lot of time. Yeah. In the final, we know our time is limited, right? 2.5 hours. Very limited. Yeah. If you spend too much time on this question, then you do not have enough time for other questions. Yeah. So you want to do it very fast, and in this way you can get the best answer. This way you can get best answer. In other ways, you spend a lot of time and you may not be able to get the best answer. Yeah. It's not easy. If you use a different way, not easy to get the best answer. Okay? Yeah. So this method, simple but very important. Okay? All right, so this is my second topic. Then the third one, yeah, so the third one here, yeah, because lower bound for this one, yeah, I gave you the formula before. Remember, log base 2 of n factorial, yeah. So I like to derive this formula, but for our final, it's not important. Okay, so for the final, it's not important. Yeah. So if some of the students are interested in this topic, how to derive I can include a video I did before. Okay, I can find my old video, so I attach to the video of this class. For other students, if you are interested, you can watch it. Otherwise, you just you can skip this one. Yeah, because how to derive it, it's not important for the final. Okay, yeah, just for your completeness of the knowledge, so you may like to know. Okay, all right. Then, yeah, we have about 20 minutes, so let me go back to the hashing part, introduction. Yeah, so I try to give you the main idea. The idea is pretty simple. Yeah, just give you the main idea of the hashing technique. Yeah, here, let me I need to go to the beginning of this file. So I like to get out of this presentation. Then move to the first page. Yeah. All right. Yeah. Let me see how far I can go in this topic. Okay. How do I get? Oh yeah. Because I need to change the color again. All right. Why using hashing? Yeah. Although our time is very limited, but I still want to explain this technique. It is very useful. Yeah. Although in the real world, you do not need to write program to implement this hashing technique. Yeah, because you should have the existing classes, methods, to help you do the work. Yeah, you do not need to write your own code. Yeah, but you need to have the basic knowledge, background knowledge for the hashing technique. Yeah. So it's the search type of problem, search type. Yeah. So we have linear search, binary search. Now I give you the third one, hashing. Yeah. How to find the data item with a given key. Yeah. So that's the typical search question, right? Yeah. You have a key. Yeah. So you store your data. So you have an array of the data. You need to find the location of the element matches the given key. Yeah. Given a collection of data dynamically. Yeah. So dynamic data. Yeah. New data keeps coming in and go. Yeah. dynamic data. All right. Each data is identified with a unique key. Yeah, the key must be unique, right? Yeah. So you can identify the data with certain key. Yeah. All right. Question: how to make your data search more efficient? Yeah, efficient. Yeah, make your data search, data search efficient. Yeah. Yeah. All right. Yeah. Yeah. Here you have freedom to choose appropriate data structure. Yeah. Because this module, our topic is an advanced data structure. So we want to choose appropriate data structure to support fast search. Yeah, our goal. Yeah. We want to get a, very fast search result. Yeah. All right. And our new data structure, we want to have this property, handle dynamic data efficiently. Yeah. All right. So here I want to do some comparison with our older methods. Yeah. All right. Linear search, binary search, then there is another search, you may not know the name. Some people call index search. Yeah. Other people call direct addressing. Yeah, direct addressing, with different names. Yeah, people call different names. Yeah. Here I use this index search name. Yeah. The data structure for these search algorithm all array. Yeah. All right. The performance, linear search, bigger of n. Binary search, bigger of log base 2 of n. Yeah. And the index search, bigger of 1. Here you can see. Yeah. What's index search? So you can imagine in a given array, yeah, each element has its own index. Yeah. Here we consider a special situation. We use the array index as the key, search key. Yeah. So given a search key, you can find the location of that element immediately because you have the index. Yeah. So in that way, the number of operations you need to do bigger of 1. That is very fast. Yeah. The following will not be, the following will not be in part B of final, but it could be in part A of final. Okay, part A, the concept questions. Yeah. So if I cover this topic, so yeah, as I mentioned, I plan to give you 5 questions from module 5 in part A, yeah, but not the part B. Okay, yeah, we have 2 parts. Yeah, that's different. Yeah. All right, yeah. So let me complete. Yeah. All right, because the thing is, this topic is a good background knowledge for you. So that's why I try to cover it. Yeah. All right. Data ordering thing, linear search, data is not ordered. Yeah. Binary search, your data must be ordered, sorted, or and index search, unordered. Yeah. All right. Yeah. Dynamic, yeah. Binary search, for the dynamic part, the cost is pretty high because you need to maintain the order. Yeah. The cost maintaining the order of the array, that cost is very high. Yeah. If you do not need to sort your data, then the cost is low. Yeah. All right. Yeah. Efficient sorting, yeah, because sometimes you may want to, look at your data in certain order, right? So you may need to sort your data. Yeah. For the linear search, if you want to sort, it's very time consuming. Yeah. For the binary search case, yeah, because the data is already ordered. Yeah. So then it's very easy. Yeah. And for other, if the data is not ordered, then so this step also time consuming. Yeah. All right. So the new search algorithm, we want to, so here, we want to, because we like this property, big of 1, so fast. Yeah. So we want to get the similar efficiency of this method. Yeah. So our goal, we want to make our search also in big O of 1. Yeah. So for other things, we can accept some, because you cannot get everything in the same package, right? Yeah. So you have to sacrifice somewhere. Yeah. Here, this place we need to sacrifice. Okay. Yeah. This place we need to sacrifice. Yeah. All right. Yeah. All right. But how to get it? Yeah. So here I want to explain the main idea, how to get it. Yeah. So let me quickly get to the points. Yeah. All right. The first thing is this index search. Not many people use it in the real world, although it is so fast, but almost it is useless in the real world situation. Yeah. Because there is a big drawback. Yeah. Very big drawback. Yeah. First, we need to understand that big drawback. Then we can improve. We can fix that big problem so we can get this new search technique, method. All right. Direct addressing, that's the index search. Yeah. So direct addressing. Key property, because you use key as the array index, a key property. So each key corresponds to each index of an array element. Yeah. But the main problem, why nobody use it in the real world? Because of this problem. Because usually the search keys are quite long in the real world applications. For example, people may use social security number as the IDs, right? Search keys, or student numbers. Yeah, many different IDs. Yeah, as the search keys, and we know for those IDs the number of digits quite long. Yeah, quite long. Okay, so that's the typical situation. Yeah, but you do not have in your array. You do not have many elements in your array. Then the problem, if you want to use this direct addressing, your array should be very large. Yeah. That's the the problem. People don't like to use that large array to store the data. Yeah. All right, waste a lot of space. Yeah. Yeah. Here the long keys. Yeah. Here I want to show you a simple example. Yeah. If we want to, store information of 40 students. Yeah, because this number very small, relatively small. Yeah. 40. Yeah. For one class already pretty big, right? Yeah. For our typical classes, pretty big. Yeah, but in general, comparing with the general data we need to process in the real world, it's a small number. Yeah. So actually, you only need an array to store 40 elements. But if you use the student number, yeah, as the array indices directly, then your array size will be very large. Yeah. So you cannot use the student number as your array indices, right? Yeah. So the main question, now we want to improve it to make it useful in the real world situations. Yeah. So the idea is how to make the keys shorter. If you can find a nice way, simple, fast, easy way to make the search keys shorter, you do not need that long array to store your data. Yeah. Then you solve the problem. So you find a new algorithm that supports fast search. Idea is so simple. Yeah. Here I just give you the idea how to make it shorter. Then that's the background of this hashing. Yeah. So that's all you need to do in your background. Yeah. All right. Yeah. Let me give you the method. So the method is we need to do some special mapping. Yeah. Map keys to slots. Yeah. So certain number of slots. Yeah. Each slot there is a number, right? Yeah. So you need to find the math functions to do the mapping. Okay? Yeah. Input is the given key, the output is the slot number. Okay? If you can find a good mapping function, yeah, so you solve the problem. Yeah, that's simple. Okay. All right. Mapping strategy. Yeah. What is a good mapping? Yeah, because when you do mapping, some mapping very bad. Yeah. So you want to avoid bad mapping functions. Yeah. So a good mapping, first it should support fast calculation. Yeah. Very fast to do the mapping operation. Yeah. You don't want to waste a lot of time in mapping. Okay. Second, evenly distributed among all the slots. Because if you map most of the keys in the restricted locations in your slots, then your performance will be very slow. So you want to spread out. The mapping locations should be ideally spread out evenly among all the slots. It could be hard. Yeah, it's not easy. Yeah, to get second property, it's not easy. Yeah, but we will try our best to get a second property. Yeah, all right. Not sensitive to any pattern. Yeah, because sometimes your data could follow some pattern. Yeah, so your mapping function should be very robust, so it can break all the possible patterns. Yeah. Break those patterns. Yeah. Okay. Still, break that means your mapping functions still work well under different patterns. Yeah. All right. Yeah. Implementation. Yeah. So here you can see the key step. You need to choose appropriate math functions for mapping. Yeah. All right. Yeah. Here I just give you two math functions methods. Yeah, here I try to use 5 minutes. Yeah, because two methods pretty simple. Yeah, I can go a little faster. Give you these two methods: division method and a multiplication methods. Yeah, yeah. Division method simple. Yeah, but not very good. Multiplication method much better than the division method. Yeah, let's look at the division method first. So when you do mapping, yeah, so M, the number of slots, okay, how to map a given key to the slot number, yeah, all right, you just do the modular operation, yeah, modular operation, so simple, yeah, that's the division method, yeah, you do integer division, but you do not take the quotient, you take the remainder, yeah, so modular operation, you just take the remainder, okay, that's simple. Yeah. All right. Easy calculation, but the performance not very good. No, not very good. Yeah. Because it is not robust. Yeah. If you have some special pattern data, then the performance will be very poor. Yeah. All right. Yeah. Yeah. So here I can use a simple example for the pattern. The pattern M number, here you can see M number is a multiple of 3 and a multiple of 5. Composite number. Yeah, it's a composite number. Okay? All right. If you do this mod operation, then think about if your data has this pattern, it's a multiple of 3. Then what would happen? If your data happens to have this property, multiple of 3, this pattern, Okay, all right. Then your hash function h of k, yeah, because after mod 15, it is the remainder also multiple of 3. Yeah, yeah, also multiple of 3. Yeah, because the remainder, yeah, yeah, because that modular operation, you have this property. Yeah. This value minus the original k, yeah, should be multiple of 15. Yeah, it's also multiple of 3. Yeah. Then your h function value is 15n minus k. K, we assume it's a multiple of 3. Yeah. Then only 1/3 of the slots can be used. 1/3, because multiple of 3, only 1/3. 3, 6, 9, 12, only these slots can be used. Other slots can never be mapped directly, right? So that's why the performance, very bad. Yeah. All right. Yeah. Make hash function robust. Yeah. So division method make function robust. Yeah. So yeah, here power of 2 also not good. Yeah. Power of 2 also not good, because if the last R bits are the same, then those keys are mapped to the same location. Okay, so we want to avoid. So good choice for division method. Yeah, yeah. So we need to. So here the property. Yeah, yeah. Here I just give you the result. Okay, all right. Yeah, all right. Yeah. So here the good property. Yeah, this is prime number not too close to power of 2. Yeah. So this way can improve the performance a little bit, but still not very good. Yeah. All right, let me use last 2 minutes to give you the idea of the multiplication method. Yeah. Multiplication method, yeah, it's much easier to get a good mapping method. Yeah. What's that? I just give you the formula. Okay, I just give you the formula, so that I can complete this topic. All right, you need to find a certain constant a between 0 and 1. Okay, yeah, because we want to control the mapping number, so we make this capital A. It's a constant. Yeah, we never change it between 0 and 1. Yeah. All right, then we do the modular operation, but your key number k multiply this A. Then it could be a larger number. Then you mod 1, you remove the integer part. You only keep the fractional part. All right? That fraction number, you multiply the slot number, n. Okay? But it may not be an integer, so you do the floor function to make it an integer. Right? In that way, the purpose is we can break the pattern. We want to break the pattern using this way to break the pattern. Okay? All right. So the good selection of A to break most pattern, that should be irrational number. Yeah. So irrational, that number can be used to break the pattern. Okay? For example, golden ratio. Yeah. Golden ratio, yeah, because it's greater than 1, we can drop this 1. Okay? Yeah, because we want to make it between 0 and 1. Okay? Then we can use this, irrational number to break the pattern. Okay? Yeah, use golden ratio minus 1 to break the pattern. Yeah. And then there are many other irrational numbers we can use to break the pattern. Okay? All right. Yeah. Yeah. The perfect hashing function, it does not exist. Yeah. People can never find a perfect hash function. So what's that perfect hash function? Always map 2 keys to 2 different slots. Yeah. So whatever hash function you use, you may have the situation you map 2 different keys to the same slot. Then that means you have a collision problem. When you have collision problem, you need to find a way to resolve the collision. So you need to do more work. Yeah. So then the high collision rate, yeah, you need to look at the percentage. Yeah. How much percent of the time you get a collision. The higher that percentage, the worse your search performance. Yeah. So you want to make your collision problem not very bad to control your collision problem. Yeah. All right, so that's the introduction of this topic. Yeah. So that's how much I want to talk about. Yeah. So this background knowledge should be, good enough for your basic knowledge, understand hashing technique. Yeah. All right. Yeah. So that's it. After you complete the homework assignment number 2 today, today deadline. Yeah. Tomorrow I need to do grading as much as I can. Then before your final, I will post the answers to this assignment. Yeah. Then in the final, you can use my answers to help you understand. Help you, work on the questions in the final. Okay. All right. So that's we complete the last class of the semester, regular class. Yeah. Then come to the classroom on Wednesday, Anheuser-Busch Hall 002 room at 5:30. Okay, I will post an announcement reminder for our Wednesday's final. Okay, all right, that's it. Yeah, see you Wednesday.